All right. I'm going to start talking about functional groups and how we use functional groups to classify organic compounds. There's four main groups that I'm going to talk about today. One of them you've already seen in the homework, but I do want to give a couple of examples of what we use them for. You might not realize, but like organic chemistry, even though like naming and drawing formulas and stuff isn't probably that important unless you're going to be going into chemistry as a major. But organic chemistry certainly is very relevant to everyday life. And as we go through each of these kinds of compounds, you'll see why. I mean, when we talked about the hydrocarbons in the last section, you know, a lot of our all of our fossil fuels, and we got like paraffin wax and what else, kerosene and things like that. All of those are organic compounds. So it is important to understand what they are and what we use them for. Probably not so important that you understand like how to name like 2,2,4-trimethyloctane or whatever. But that's just part of, I guess, the curriculum or whatever. So now we're going to be looking at functional groups. Now, all the way back in grade 10, almost I think like the first or second unit that I taught you guys, I mentioned functional groups, and it's an atom or group of atoms that has a particular property. And when a compound has this functional group, it will take on that property. And way back in the day in grade 10, the biggest functional group I talked about was hydroxyl, which is OH. And that has the property of being polar. So when you have OH in a compound, the compound then becomes polar, at least in that area of the compound. I mentioned that when we talked about fatty acids and how when you have triglycerides, you've got fatty acids, which are long hydrocarbon chains. And at one end, you have a carboxyl group. Carboxyl is another functional group that's COOH. Pen out, there we go. So COOH, that is another functional group. This is actually going to become a group of organic compounds called carboxylic acids, which I'll get to later, probably next week. But in the context of what I talked about 2 years ago in fatty acids, this was one end of the fatty acid, and the rest of it were hydrocarbons. So those are all carbons and then hydrogens everywhere. So this made this end of the molecule polar, mostly because of this OH here. This end was non-polar. And especially if you think about phospholipids, oops, this is glycerol, which is polar. And then your hydrocarbon tails, which are the same, these two ends are the same, non-polar. So when you talk about the cell membrane, you have to have a bilayer. Oh, Fennec is here. You have to have a bilayer so that, sorry, I'm just keeping attendance. Oh, and now that, all right, everyone's here, yay. Right, so yeah, so you have a bilayer to protect your, oh, my drawings are gone now. Phospholipids. So you have your non-polar tails and your polar heads. And all of that is chemistry, even though we talk about it in relation to biology. Okay, so the first group that I want to talk about, which you have already seen, like I said, in the homework, because you had some of the halogens that were attached to your hydrocarbons. These are called alkyl halides. Now, alkyl, because it's a side chain, and halides comes from halogens. And you guys already know how to name those, so I don't have to worry about that. But just as a review, if we look at this molecule down here, we have 2 carbon atoms, so that's F. They're all single bonds, so it's ethane. And we have 1 chlorine, and we have 2 bromine. So chlorine comes after. So it's chloro and dibromo. And then you number them. So you do 1 dibromo, 2 chloroethane would be that one. But that's not what I wanted to focus on, because you guys have already figured out how to do that. But now you know they're called alkyl halides. You already know that. I just wanted to get to the part where we care why. Come on. There we go. So why do we care about alkyl halides? Well, they are some of the most widely used organic chemicals, probably the most infamous. If you don't know the difference between famous and infamous, being infamous is like being famous, but for something bad, right? So if you're famous, everybody knows who you are. But if you're infamous, it's because you're well known because of something bad. So an infamous alkyl halide is CFCs. These contain chlorine and fluorine. The most commonly used CFCs are Freon 11 and Freon 12. So Freon 11, we have trichlorofluoromethane, and Freon 12 is dichloro-difluoromethane. Has anybody heard of CFCs before? I take the silence as a no. Okay. Well, they are both odorless, non-toxic, and non-flammable. They're also very stable. So you might think, that sounds pretty good. They also change physical states very easily, which makes them useful in commercial operation. They are used in the manufacture of plastic foam, and probably the most well-known use of them is as refrigerants in refrigerators. The height of production of CFCs in 1985, there were 700 million kilograms manufactured worldwide. So far, so good. Seems like they're pretty useful. If they're non-toxic, non-flammable, really stable, seems fabulous. So here is a sub-zero freezer. Sub-zero freezers are the big, giant, long freezers that sit on the floor, and then you open them up from the top. And you can see here's a Freon leak. But Freon is the gas that's used in refrigerators and freezers to make it cold. The reason why they are infamous is because these are the #1 chemical that destroys the ozone. When CFCs are released into the atmosphere, they break down and they release free chlorine atoms. And if you remember or have learned anything from me in chemistry, you should know that chlorine is an extremely reactive atom by itself, because it needs only 1 electron to be stable. So through solar radiation, here's Freon 12, that's dichloro-difluoromethane, and it releases 1 chlorine atom. Now, if you know anything about the halogens, usually you see chlorine as a diatomic molecule, Cl2, but in this reaction, it's not Cl2, it's just a single chlorine atom. So that's going to be desperate to gain an electron. When it gets up into the upper atmosphere where the ozone layer is, it's going to attack the ozone and convert ozone into oxygen. And so here's that equation. You've got chlorine plus ozone. You're going to make a chlorine monoxide and oxygen gas. And therefore it depletes the ozone, breaks it down. It's even worse than that, because eventually the chlorine atoms are regenerated. So the chlorine monoxide is going to react with single oxygen atoms and release that re-release that chlorine and form oxygen gas. So just 1 chlorine atom can destroy thousands of ozone molecules. And imagine, again, back in 1985, I know you guys weren't born yet, but I was a little girl and everyone was using CFCs. And so you've got 700 million kilograms being produced every year. We're pumping that into the atmosphere, not realizing that we're destroying the very layer of the atmosphere that protects us from getting skin cancer every year. Now, I do think that the situation has improved. I haven't read some of the latest research, but I do think I recall reading somewhere that the quote unquote hole in the ozone, which isn't really a hole, but it's a thinner layer concentrated over Antarctica. I think I read it was getting better, but I have to double check on that anyway. So why that's important is because the ozone is what protects us from the damaging radiation from the UV light from the sun. The ozone layer prevents most of the UV light from reaching Earth. And in 1987, there were over 100 nations that signed an agreement to reduce their usage of CFCs. So here's a picture. It doesn't say what year this is from. Oh no, 1996. There we go. So that was a good 25 years ago. So obviously you see the scale here. And so you can see how it's much thinner above the Antarctic. And even just that depletion of the ozone, even though it's at the South Pole and nobody lives at the South Pole, and no humans live at the South Pole, that depletion is still responsible for like 100,000 cases of skin cancer per year. All right, so again, for the alkyl halides, they are widely used. They are not miscible with water, but they are more dense. Here's Freon 11. And it's also used as an aerosol propellant. And what that means is basically if you have an aerosol can, any kind of can like hairspray that goes and it's not like a pump thing where you got to pump it each time, you just push the button and air continuously comes out. Those often use CFCs, although like I said, I think most countries have tried to switch to something different. Now, one of the most interesting uses of alkyl halides is in the development of a substance called Teflon. Now, the technical name for Teflon is tetrafluoroethane, ethene. So that would be, there's ethene, tetrafluoro, oops, that's supposed to be an F. There you go, Teflon. You join this in long chains and you make something called Teflon. Now, Teflon is pretty much one of the modern miracles as far as cookware is concerned, because it forms the non-stick layer on the bottom of your pots and pans, because the carbon fluoride bond makes it inactive, the chemical, so it doesn't react with food when you're cooking it. It also is stable up to 325 degrees Celsius, which is pretty freaking hot. And the most useful property of Teflon is it has a low coefficient of friction. So this allows all of your food to slide smoothly. If any of you have a cast iron pan, you'll know because it's going to be heavy as hell. I have one from IKEA, which I use to cook steaks and stuff like that. But it's really hard to get things off the bottom of an iron pan because it's not non-stick. So every time you see, like in the grocery store or at the mall or something, now that those are open again, and you go through the pans and you'll see like non-stick surface or whatever, that's Teflon. We also use it in machine parts that we can't lubricate with things like oil or silicone products. So there you go, Teflon. All right, so that was the one that you already knew kind of how to integrate the naming, but I wanted to make sure that I gave you like real world uses for it. On to the next group, which are the alcohols. Now, the defining functional group. Now, remember, I did start this by saying these groups are going to be classified according to their functional group. So you're going to have something to look out for in order to determine which type of compound it is. For alcohols, it's hydroxyl. So you're going to be looking for OH. Here's OH, OH, OH. Or is it there? This one's a diol and a triol. Okay, so the general formula for an alcohol would be R-OH. The R stands for basically the hydrocarbon part, so it doesn't matter what how many carbons are there. But what we're looking for really is the OH there. And that tells you it's an alcohol. And like everything else, there are rules for naming alcohols. So rule number 1 is you're going to locate the longest parent chain that contains the hydroxyl group. So it's the same kind of thing where before I talked about the alkenes and the alkynes, the double bond, the triple bond takes priority. You have to find the longest chain that contains those bonds. Now that we have functional groups, of course, the functional group has to be part of the parent name. We're going to use the alkane name. So like methane, ethane, propane, like that. We're going to drop the E and change the ending to -ol. In my mind, it's a little bit easy to remember this because it's alcohol and you're using the same ending. So for example, if I have 1 carbon and 1 hydroxyl group, this tells me it's an alcohol. 1 carbon, which is meth, methane becomes methanol. Methanol. You might have seen that in the lab. And if you have 2 ethanol, this is the alcohol that we drink. Yeah. We do not drink methanol because methanol attacks your optic nerve and you go blind, which is one of the dangers in trying to distill your own alcohols at home, especially harder alcohols like whiskeys and vodkas and things like that, that you can accidentally end up making some of it methanol, and that, like I said, it can make you go blind. If there's more than 1 hydroxyl group, then of course you put a di or a tri or tetra, whatever, in front of the ol in order to indicate there's more than 1 hydroxyl group. And of course, the position numbers are going to be given to the functional group. Oops. So you're going to number the carbon atoms in the chain so that the hydroxyl groups, I know I've got writing all over, but the hydroxyl groups have the lowest number possible. So it's really going back to the very beginning when we talked about alkanes, and the only thing that you add to all single bond hydrocarbon are the alkyl groups. So the alkyl groups get the lowest position number. However, once you start adding double bonds, multiple bonds, double, triple bonds, or functional groups, that is what defines the parent compound. That is what gets priority for numbering the carbon chain. So you're going to place the hydroxyl position number or numbers immediately before the name of the parent alcohol. Of course, you can always do the way that I showed you last week, which is putting it right before the suffix. So you could have butan-2-ol or 2-butanol, depending on whichever one you were comfortable with. Okay, and then of course, punctuation. So for example, this one is called 1-propanol or propan-1-ol. For propanol, you absolutely have to have position number because you could have the hydroxyl on the first one, which would also be that one, because of course, remember, you can flip it. But most importantly, it could be on the middle one, which would make it a completely different compound, right? That would be an isomer. If you have 2-propanol, it looks completely different. So here's the hydroxyls in the middle, but on 1-propanol, if you draw it that way, and then a little one OH there. Okay, those are isomers. This one, 2-butanol. Again, you just have the parent chain where the hydroxyl is on that chain. You're not actually obviously going to go through the hydroxyl because it doesn't contain carbon. And another one, this one is 2,2-butanediol. So here's the only difference. And this is getting really picky, but I need to make sure that I inform you of all of the rules. If it's a diol, triol, tetrol, etc., you keep the E from the alkane name. Okay, it's not butanediol, butanediol. And I think it's just a matter of, I don't know, maybe it sounds better. I'm not really sure why they get rid of the E or I mean, butanol, I guess, is just weird to say. So butanol is more smooth, I guess. I don't know. But butanediol, I guess, is a bit more difficult to say. Okay, so what do we use alcohols for? Well, besides drinking and feeling really good, we have boiling points, comparing them to the alkane of a similar molar mass. So we have methanol versus ethane. And the molar mass you see here, 32 and 30. There's a difference between the boiling point of 64.7. Look at this, compared to negative 88. So ethane boils at negative 88 degrees Celsius, but methanol doesn't boil until 64.5 or 64, 65, whatever degrees. And the only reason for that is this bad boy right here. Because what happens when you have a molecule that's polar? You're going to end up having hydrogen bonds, exactly like what I taught you in the very beginning. When you have polarity, there are certain properties that stem from polarity, and one of them is cohesion. They stick together. You have hydrogen bonds. That's going to make your melting points and your boiling points increase dramatically. That's why I said for the last 2 years, if I ever ask you anything about why water is special, the first thing I want you to say is it's polar. Well, who cares? That gives us really unique properties like temperature moderation. The reason why all living things on the planet are made mostly of water is because it helps to modify temperature, because the environment is always changing. We don't want the changing environment to have a huge effect on the internal environment of our bodies. And so if it's mostly water, changing temperature won't have that much of a difference. So that's all due to hydrogen bonding because of polarity. And of course, it would make sense that if you increase the number of hydroxyl groups, you're going to increase boiling point even more, because you will increase the number of hydrogen bonds. You should know why already. So if you have ethanol that has one hydroxyl group versus 1,2-ethane diol, so you've literally only added one hydroxyl group more, and you more than almost triple, not more than, but you almost triple. Is it 80? No, definitely double. You more than double the boiling point. Okay, and if you go from 1 to 2 to 3 down here, you go from 98 to 97 to 188 all the way up to probably 260, just by adding one more hydroxyl. That tells you the power of the polarity of the hydroxyl group. Okay, hydrogen bonding, explained that already. And another property of alcohols, because they are polar, they will dissolve in water. But the solubility is going to decrease with the size of the solubility is going to decrease as the size of the molecule increases, because as the size of the alcohol increases, the non-polar hydrocarbon parts are going to get bigger. Okay, the hydrocarbon chain is non-polar, so the bigger that hydrocarbon chain is, the less soluble it is. So here you've got methanol, which has only one carbon, completely soluble. If you go up to octanol, solubility is only 0.06 grams per 100 grams of water. So the more carbon hydrogen bonds you have, then the less soluble it is. The hydrogen bonding in alcohols also explains its other properties and uses. For example, in cold creams, lipsticks, body lotions, etc. Alcohols are used heavily in cosmetics because they have this hydrogen bonding. Because of the polarity, it helps in products where moisture is a benefit. If you don't know what cold creams are, they're basically like instead of using like a facial foam or a facial soap or gel or something that gets really sudsy, it's like a thick cream that probably your grandmas, I would guess, would use, and they would just put even straight just on their makeup. It's a makeup remover. Now we see things like micellar water, if you've seen that. Micellar, oops. and you can use those as makeup removers. I got a bottle upstairs. It's kind of like this watery but kind of oily type thing. And that's to help remove makeup, because a lot of makeup, it doesn't really dissolve well with regular facial cleansers, because they're polar. So you need to use things that have more of like an oily texture, especially things like waterproof mascara and stuff like that. It's really hard to get off with regular soap and water. So glycerol, which you should recognize, glycerol is the backbone of the triglycerides. And this is glycerol. And so for your fatty acids, your 3 fatty acid chains would come off of that. And glycerol is technically named 1,2,3-propane triol. And that helps to keep moisture in. And again, the more hydroxyl groups there are, the higher the water retention. So that's why they use a triol and not just a singular hydroxyl group alcohol. And of course, we have gasohol. Ethanol is combined with gasoline in a 1:9 ratio to make gasohol. Gasohol burns more cleanly. It helps to save our petroleum reserves. It helps to reduce our dependence on oil, not our independence. But the problem is it only produces 60% as much energy per gram as gasoline does. And so that's why it's very difficult to try to get industries to move away from gasoline, because there are no alternate energy sources that are as energy, as energy rich. There's no other source of energy that gives us as much energy as gasoline does. And ethanol increases the water absorption in fuel, which is not good. You don't want water in your fuel. All simple alcohols are slightly poisonous. Yes, even the kind that we drink. When ethanol is consumed, it is broken down by an enzyme called dehydrogenase. This converts ethanol to acetaldehyde, which is then converted into acetic acid. Now, the lethal dose of ethanol varies with the individual. A liter of hard alcohol, because hard alcohols like your vodka, gin, whiskey, bourbon, things like that, they are 80 proof. So the way that we measure the alcohol content of alcohols that we drink is by something called proof. And in general, I don't know, not the proofness, but the total proof is going to be half of the percent. Sorry, double. The percent is half. Double the percentage of alcohol. So if you go to the grocery store and you look at the side of the bottle and you pick up some whiskey, you'll see it's 40% or 80 proof. And so if you drink a liter of hard alcohol, you're literally ingesting 400 milliliters of ethanol. And that, I would say, for most individuals, that would be fatal. The only individuals it wouldn't kill are probably people that drink a whole hell of a lot of alcohol on a very regular basis. Other simple alcohols are attacked by alcohol dehydrogenase more slowly, and that makes it more toxic than ethanol. Now, methanol is converted to formaldehyde. If you don't know what formaldehyde is, that is literally the liquid that we use to embalm dead people. Because I know in Thailand you cremate almost everybody, but in Western countries, for some reason, we like to take all of the fluids out of a person and pump them full of formaldehyde so that we can go and like stare at them for a few days during the wake, and then we bury them under the ground. I don't know why, but that's just, I mean, for me, I'm like, just burn me up and whatever, like, who cares? I'm dead. I'm not going to care. Anyway, and then formaldehyde eventually turns to formic acid, and both formaldehyde and formic acid are toxic. This is why I said methanol is bad. It's 10 times more toxic than ethanol. And like I said, it damages the optic nerve. It can lead to coma and even death. Okay, so that's just kind of a general breakdown of alcohols. And I see it's 10 after 2 already.